if you're watching the live stream, please don't forget to comment on the presentations. I'd now like to invite, Andreas Kaisaris, who is representing the UK, to the stage. Please join me in welcoming Andreas.
Hello everyone, and thank you for coming. Before I start getting into the details of my presentation and start talking about this amazing piece of engineering called the James Webb Space Telescope, I think it's important that we ask ourselves a very important question. That is, why explore space? We have so many problems down to Earth, global warming, hunger, war. Why should we spend all this money, time and effort here going to space when we could be spending the same amount of time and effort here on Earth? I think the real question here is, why explore at all? I believe simply the answer, it's in our DNA. As we are the descendants of people that were curious and that they explored the environment. And I think we need to continue doing that. Luckily, human beings are actually quite good at developing tools that allow them to explore their environment. We've traveled across the largest oceans and the tallest mountains, but Earth wasn't enough. Earth was never enough. We were always intrigued by the unknown, and space was one of them. It was 1608 in Netherlands when Hans Lippershey invented the first telescope. Of course, in the beginning, it was only used in battles and to spot the enemy. His design was consisted of 2 lenses, and his subject would only look around 3 times magnified. News of the refracting telescope spread rapidly through Europe, where engineers and physicists created their own version of the telescope, but this time they used it to look up in space. It wasn't until 1674 that Isaac Newton completed his groundbreaking research and presented to the world his all-new design of the telescope. He called it the reflecting telescope, as he had replaced the lenses with curved mirrors. If only he had known that technology that he had just invented would be the basis to most modern telescopes today. Today, telescopes are bigger, as a larger mirror gives you a better resolution. We've put our biggest telescopes to tall mountains to try to get above the Earth's atmosphere that blurs and obscures the objects that we're trying to observe. But no matter how tall the mountains are, we still have to deal with the atmosphere. So what do? We send telescopes to space. And of course, out of all of the space telescopes, the Hubble Space Telescope is by far the most famous, as it has been to space for almost 30 years, as it was launched in 1990. Its images have captivated the world, and it has taught us so many things about the universe. And most importantly, it has given us the rough size of the universe with just this photo right here. So after all this time, and after all the things that Hubble has taught us, it's time that we move to something more powerful. It's time for the James Webb Space Telescope. Webb will be the successor to Hubble, as it is designed to answer astronomy's biggest questions today, the questions that Hubble just couldn't quite get to. Webb is divided into 2 sides by the sun shield membrane. The cold side contains instruments like the cameras that take in the light from the mirrors, the spectrograph that analyzes the data, the guidance sensor that makes sure the telescope is pointing where we want it to point, and of course the 2 mirrors. The large mirror, which is made out of 18 separate octagonal segments that can all be manipulated to reflect the light straight into the second, a smaller mirror, which then reflects light straight into the filters of the camera, of the telescope. The hot side, that could reach up to 80 degrees Celsius, contains the solar panels that act as the energy source of the telescope, the communication antenna, the computer, that is the brain of the telescope, and of course, the steering mechanisms like jets and steering wheels. Webb is different from Hubble, though, in a few key ways. The first key difference is the size. Webb will be by far the biggest telescope ever sent to space. Hubble is around the size of a large truck. From top to bottom, Webb will stand 3 stories tall and will be as wide as a tennis court. The second key difference is the place in space where Webb will be. Hubble orbits the Earth around 350 miles up, relatively close. Webb will be sent at 1 million miles away from Earth. That's 4 times further than the Moon. An Ariane 5 rocket will be used for the launch, and it will take a full month to reach its final destination, where it would start orbiting the Sun while staying in line with Earth for the communication. The reason it's going to be sent so far away from Earth is so that it can get cold, which leads me to the third and final key difference, which is the type of light that Webb will see. Hubble is a visible light telescope. This is optical light, something that your eyes, for example, could see. Webb will see the universe in a complete new light. It will see it in infrared light. Infrared light is a bit more red than your eyes could see. Here's a hint of what we might expect to see with Webb. Believe it or not, development of the Webb started in 1996, with an initial launch date in 2007. Of course, this date has been pushed back again and again, with the current launch date in March of 2021. Why does it take so long for the telescope to get in operation? Well, it's a bit complicated. Most of the delays have been caused by the design specifications themselves. For instance, there is no current launch craft that could fit a 6.5 meters wide mirror. For that reason, the mirror was designed in a way that can fold away during launch. The second challenge was the weight of the mirror. If the same material that was used for the Hubble mirror was used for the Webb, it would make it impossible to be delivered to its final destination. For that reason, engineers use beryllium as the main material, which is both very strong and very light, and they cold-plated it for the reflective surface. The third and final challenge that they had faced was the excess heat. Infrared light telescopes are extremely sensitive to heat, even heat created by the telescope itself. For that reason, a radiator was designed to radiate the heat that it creates. But of course, the main source of heat in our solar system is the sun. And to counteract that, engineers designed the sun shield membrane. 5 layers of it, in fact, each thinner than a human's hair. Again, due to launch limitations, the sun shield will start folded away during launch until the telescope reaches space, where it's going to start carefully and slowly unfold during the course of 2 days until it's fully stretched out. You can imagine the amount of planning and testing that this procedure had to go through to make sure that when the telescope is out there, everything will go according to plan. So after all this wait, and after all this time, what do we accept to observe with the telescope? And what are its limitations? First thing that we want to observe are the first galaxies ever created after the Big Bang. Telescopes are basically time machines. They allow us to see objects of how they were in the past. Of course, that doesn't mean that if I had a telescope right here in front of me and I was looking right through it to you, that I would see you as babies. Unfortunately, that's not how it works. It only works with objects very far away into space, as the light from these objects takes time to travel through space to reach our telescopes, and therefore, the further away we look into distance, the further back we look into time. We're talking about looking at 13.5 billion years in the past. The second thing that we want to observe are how these first galaxies were formed and how the stars inside them were actually created. You can imagine information like that would be extremely useful for us and valuable, as they would answer so many questions about our own galaxy and our own solar system. The final thing that we want to observe, and the most interesting in my opinion, are exoplanets. What are exoplanets? They are simply planets outside our solar system. What do we want to observe from these planets? We want to look at the top thin layer of the planet as their parent star shines through the atmosphere. That's where the spectrograph comes to play. We will compare the color of the atmosphere with the light spectrum and find out the planet's composition. And who knows, one of those planets might end up being a new home. If that's not exciting, I don't know what it is. It turns out that all these science fiction movies are not so science fiction after all. To close off, I would like to show you some photos taken by previous telescopes. What's incredible with these photos is how mesmerizing they are. We've all seen a beautiful sunset, an exotic beach somewhere in Indonesia, which are great, don't get me wrong, but looking at these nebulas, it's something different. There's something that connects us. No matter what language you speak or where you're from, when we're looking out there at the cosmos, we are one. We are humans, and this is our world and for us to discover. Thank you very much for your time.
Thank you, Andreas. We now come to the achievement medals.